There is a particle that is, in almost every measurable way, identical to the electron. It carries the same electric charge. It obeys the same fundamental forces. It even spins at the same rate. If you wrote down the laws of physics for the electron and then handed them to this particle, it would follow every single one without complaint. Except for one detail. It is 207 times heavier. And because of that single difference, that extra mass, it does something the electron never does. It dies. In about 2 millionths of a second, it simply falls apart. The question is why? What is it about being heavier that makes a particle unstable? What is this particle actually made of, if anything at all? And why does the universe even bother creating something so perfectly designed to destroy itself almost immediately? Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that happened in the 1930s, because that's when this whole mystery began. Physicists at that time thought they were close to understanding everything. They had the electron, a tiny, negatively charged particle that orbits the nucleus of every atom. They had the proton, positively charged, sitting in the nucleus. They had the neutron, which had just been discovered in 1932, also in the nucleus, carrying no charge at all. And they had the photon, the particle of light that carries the electromagnetic force between charged objects. 4 particles. That was supposed to be it. That was supposed to be the full inventory. Everything you could see, everything you could touch, every star and planet and grain of sand, all of it built from just these 4 building blocks. It was clean, it was elegant, it was beautiful in the way that physics is supposed to be beautiful, where a small number of rules explain a vast number of phenomena. And then somebody found something that didn't fit. In 1936, 2 American physicists named Carl Anderson and Seth Neddermeyer were studying cosmic rays. Cosmic rays are high-energy particles that come streaming in from space, mostly protons and heavier atomic nuclei, travelling at enormous speeds. When these particles slam into molecules in Earth's upper atmosphere, they produce showers of secondary particles, debris from the collision that rains down through the atmosphere. Anderson and Neddermeyer were using a device called a cloud chamber to study these secondary particles. A cloud chamber is essentially a sealed container filled with supersaturated vapour. When a charged particle flies through the vapour, it ionizes the gas molecules along its path, leaving a visible trail of tiny droplets. You can photograph these trails, and by placing the chamber in a magnetic field, you can measure how much the trail curves. The amount of curvature tells you 2 things simultaneously. The direction of the curve tells you the sign of the particle's charge, whether it's positive or negative. And the tightness of the curve tells you something about the particle's momentum, which depends on both its mass and its speed. Anderson and Neddermeyer kept finding tracks that didn't belong to any known particle. The tracks curved the wrong amount. They curved more than a proton's track would at the same speed, which meant the particle was lighter than a proton. But they curved less than an electron's track would, which meant the particle was heavier than an electron. The charge was negative, like an electron. The behaviour was like an electron, but the mass was wrong. Whatever this particle was, it sat right between the electron and the proton, too heavy to be one, too light to be the other, and nobody had predicted it. Nobody had asked for it. There was no gap in the existing theory that this particle was supposed to fill. This particle was uninvited. It showed up to the party without an invitation, and nobody knew what to do with it. At first, there was enormous confusion about what this particle actually was. A Japanese physicist named Hideki Yukawa had recently predicted the existence of a particle with a mass between the electron and proton, but Yukawa's particle was supposed to be the carrier of the strong nuclear force, the force that holds protons and neutrons together in the nucleus. So naturally, people assumed Anderson and Neddermeyer's new particle was Yukawa's predicted particle. They called it a mesotron, later shortened to meson, meaning middle, because its mass sat between the electron and the proton. But something was wrong. Yukawa's particle was supposed to interact strongly with atomic nuclei. That's the whole point. It was supposed to be the glue holding the nucleus together. But this new particle barely interacted with nuclei at all. Experiments showed it could pass through enormous amounts of matter without being absorbed. It would sail right through blocks of iron and lead as if they weren't there. That's not what a nuclear force carrier should do. A nuclear force carrier should be grabbed immediately by any nucleus it passes near. This particle was essentially ignoring nuclei entirely. It took about a decade to sort out the confusion. In 1947, Cecil Powell and his team at the University of Bristol discovered another particle in cosmic ray experiments using photographic emulsions. This new particle did interact strongly with nuclei, exactly as Yukawa had predicted. This was the real Yukawa particle, and it was named the pion. The particle Anderson and Neddermeyer had found was something else entirely. It wasn't a meson at all. It wasn't a carrier of any force. It was a completely different kind of particle, one that belonged to the same family as the electron. It was eventually named the muon. The muon is not a meson. This is a historical distinction that matters because the name originally suggested it was something it isn't. Early physicists called it the mu meson, but that name was misleading. A meson, as we now understand the term, is a composite particle made of a quark and an antiquark bound together by the strong force. The muon is not made of quarks. It doesn't feel the strong force at all. It's a fundamental particle, indivisible as far as every experiment has ever shown, belonging to the same family as the electron. That family is called the leptons. Now this is where things get genuinely strange, and this is the heart of what we're exploring tonight. When physicists finally figured out what the muon was, they discovered something profoundly unsettling. The muon is essentially a heavier copy of the electron. Not roughly similar, not approximately the same. It appears to be identical in almost every property except one. The muon carries the same electric charge as the electron, -1 elementary charge. It has the same spin, 1/2, which classifies it as a fermion. It interacts through the same forces, the electromagnetic force and the weak nuclear force. It does not feel the strong nuclear force, just like the electron. If you wrote down every rule that governs how the electron behaves, every equation describing its interactions with photons and with the weak force carriers, and then you simply replace the electron's mass with a larger number, you would get the muon. The muon follows the same rules. It obeys the same symmetries. It plays the same role in every equation. It's the electron's script performed by a heavier actor. The only difference, the only distinguishing property, is mass. The electron has a mass of about 0.511 mega-electronvolts divided by the speed of light squared. The muon has a mass of about 105.7 mega-electronvolts divided by the speed of light squared. That makes the muon approximately 206.8 times heavier than the electron. And this is not a small difference, this is enormous. If the electron were a house cat, the muon would be a full-grown tiger. Same species, same basic body plan, same number of legs, same predatory instincts, but vastly different in scale. And here's what makes it deeply strange. Nobody knows why. This might be the most overlooked, unsolved problem in all of physics. We have no explanation for why the muon has the mass it does. We have no explanation for why the universe contains a heavier copy of the electron at all. The standard model of particle physics, which is our best and most precisely tested theory of fundamental particles and forces, can accommodate the muon perfectly well. The mathematics works. You can plug the muon into the equations and everything is self-consistent. But the standard model doesn't predict the muon. It doesn't explain why it exists. It doesn't tell you why its mass is 207 times the electron's mass, rather than 50 times or 1,000 times, or exactly the same. The muon's mass is simply a number that has to be measured experimentally, and then entered into the equations by hand. The theory accepts it. The theory does not explain it. So what is the muon made of? This is a question that sounds simple, but opens up something very deep. When most people hear the phrase "made of," they think of composition. What's a cake made of? Flour, eggs, sugar, butter. What's the ocean made of? Water molecules. What's a proton made of? Quarks and gluons. In everyday life, and even in much of particle physics, asking what something is made of means identifying smaller, more fundamental components inside it. And for many particles, this is exactly the right question. A proton is made of 2 up quarks and 1 down quark, held together by gluons, the carriers of the strong force. You can probe a proton with high-energy electrons and actually see the quarks inside. They scatter off the internal structure, revealing the proton's composition. A neutron similarly contains 1 up quark and 2 down quarks. These particles are composite. They have insides. But the muon, as far as every experiment has ever determined, does not have insides. There is no internal structure. When you fire high-energy particles at a muon and watch how they scatter, you find behavior consistent with a point particle, an object with no spatial extent, no subcomponents, no building blocks smaller than itself. The muon is not made of quarks. It's not made of smaller leptons. It's not, as far as we can tell, made of anything. It is itself, fundamental and indivisible, an elementary particle in the fullest sense of the term. The same is true of the electron. The electron has no known internal structure either. Both particles appear to be genuine point particles, zero-dimensional objects with mass and charge and spin, but no physical size. This might seem strange. How can something have mass but no size? How can something exist without being made of anything smaller? But this is how fundamental particles work in modern physics. They are not tiny balls. They are not little spheres with surfaces and interiors. They are excitations of quantum fields. And understanding what that means is crucial to understanding what the muon actually is. In modern physics, the most fundamental description of reality is not a description of particles at all. It is a description of fields. A quantum field is something that exists at every point in space and time. It pervades the entire universe. You can think of it loosely as an invisible fabric stretched across all of reality, capable of vibrating. When the field is in its lowest energy state, its ground state, nothing appears to be happening. The field is calm. There are no particles. But when energy is added to the field, when it is disturbed in the right way, it can develop localized vibrations, ripples of energy that behave exactly like particles. These ripples move through space. They carry energy and momentum. They interact with other fields. They are, in every measurable sense, what we call particles. But fundamentally, they are not independent objects floating through empty space. They are disturbances in a field. The electron is an excitation of the electron field. Wherever the electron field vibrates with enough energy and in the right way, an electron appears. The photon is an excitation of the electromagnetic field. Wherever that field oscillates, a photon exists. And the muon is an excitation of the muon field, which is a separate field from the electron field. This is a critical point. The electron and the muon do not arise from the same field. They come from different fields, distinct quantum fields that happen to share many mathematical properties. The electron field and the muon field have the same charge structure, the same spin structure, the same coupling to the electromagnetic force and the weak force. They are mathematically almost identical fields, but they differ in one crucial respect. The muon field couples more strongly to the Higgs field than the electron field does, and this is what gives the muon its greater mass. The Higgs field is another quantum field that fills all of space. Unlike most fields, the Higgs field has a non-zero value even in its ground state. Even in a perfect vacuum, the Higgs field is not zero. It has a constant background value everywhere. When other particles move through this background, they interact with the Higgs field, and this interaction is what gives them mass. The stronger a particle couples to the Higgs field, the more mass it acquires. The electron couples weakly to the Higgs field, so it has a small mass. The muon couples more strongly, so it has a larger mass. The top quark, the heaviest known fundamental particle, couples extremely strongly, giving it a mass roughly 340,000 times greater than the electrons. This is the mechanism by which fundamental particles acquire mass in the Standard Model. It's not that the particle is built from heavier ingredients, it's that the particle's underlying field interacts more intensely with the Higgs field, and this interaction manifests as what we experience as mass. The muon is heavier than the electron because the muon field grips the Higgs field more tightly. But here's the thing that keeps physicists awake at night. The Standard Model doesn't explain why the muon field couples to the Higgs field more strongly than the electron field does. It simply says that it does. The coupling strengths, called Yukawa couplings, are free parameters of the theory. They're numbers that have to be measured and inserted. The theory provides the framework, the mathematical machinery, but it doesn't generate these numbers from first principles. It's as if you had a recipe that says, add the right amount of salt, but never tells you how much salt is the right amount. You have to taste and adjust every time. For the Standard Model, the masses of all the fundamental particles are like that. They're not derived, they're observed. This is deeply unsatisfying for physicists who believe that a truly fundamental theory should have fewer free parameters, not more. The Standard Model has about 26 free parameters, including the masses of all the quarks and leptons, the strengths of the three forces, and properties of the Higgs field. Many physicists suspect there is a deeper theory beneath the Standard Model, one that would explain these parameters, one that would tell us why the muon is 207 times heavier than the electron instead of some other number. But we haven't found that theory yet. Let me come back to the question of what the muon is made of, because there's a subtle but important point that needs to be absolutely clear. When we say the muon is a fundamental particle, we mean that as far as every experiment ever conducted has shown, the muon has no internal structure. But this is a statement about current knowledge, not an eternal truth. History has a pattern here. The atom was once thought to be fundamental. The word atom literally means indivisible. Then J.J. Thomson discovered the electron in 1897, showing atoms had internal parts. Then Rutherford's gold foil experiment in 1911 revealed the nucleus. Then protons and neutrons were discovered inside the nucleus. Then quarks were found inside protons and neutrons. Each time, what was thought to be fundamental turned out to be composite, built from smaller pieces. Could the muon be next? Could it too have internal structure at some scale we haven't probed yet? It's possible. Some speculative theories, known as preon models, propose that quarks and leptons are made of even more fundamental particles called preons. In these models, the muon might be a different arrangement of preons than the electron, and the different arrangement might explain the mass difference. But preon models have serious problems. They struggle to reproduce the known properties of quarks and leptons without introducing new difficulties. And there's no experimental evidence for preons whatsoever. No experiment has ever detected any hint of internal structure in the muon or the electron. Particle accelerators have probed down to scales of about 10 to the minus 19 meters, roughly 10,000 times smaller than a proton. And at those scales, both the muon and the electron still look like point particles. So while we cannot rule out the possibility that the muon is composite, the current evidence strongly favors the muon being genuinely fundamental. It appears to be a particle that is not made of anything else. It simply is what it is, a fundamental excitation of its own quantum field. This brings us to the central paradox that everything else in this story depends on. If the muon is a fundamental particle, if it has no internal structure, if it is truly elementary, then why does it weigh what it weighs? And even more importantly, why does the universe bother having it at all? The electron does everything the muon does. Every role the muon could play in atomic physics, in chemistry, in the structure of matter, the electron already fills. The muon seems redundant. It's a duplicate, a photocopy of the electron, made heavier for no apparent reason. In most physical situations, the muon doesn't even get to participate because it decays almost immediately, vanishing in about 2 millionths of a second. It's as though nature built a perfectly good particle, the electron, and then made a second version of it that's too heavy to stick around. And the muon is not the only case of this strange duplication. In the Standard Model, Every fundamental particle comes in 3 copies, called generations. The electron is the lightest charged lepton. The muon is the next heaviest. And there is a third, even heavier copy called the tau, heavier still, the heaviest charged lepton by a wide margin. The same pattern holds for the quarks. The up and down quarks, which make up protons and neutrons, are the first generation. The charm and strange quarks are the second generation, heavier versions of up and down. The top and bottom quarks are the third generation, heavier still. And the same is true for the neutrinos, the uncharged leptons. There is an electron neutrino, a muon neutrino, and a tau neutrino, each associated with its respective charged lepton. 3 generations of matter, 3 copies of the same basic pattern, each heavier than the last. And nobody knows why there are 3. Not 2, not 4, not 1, 3. The standard model accommodates 3 generations, but doesn't predict the number. It could work with any number. 3 is simply what nature chose, and the reasons remain hidden. This generational structure is one of the deepest puzzles in all of particle physics. It is sometimes called the flavor problem, or the family problem, and it has resisted explanation for decades. Every attempt to explain it has either failed or introduced new questions as difficult as the original. Supersymmetry, grand unified theories, string theory, extra dimensions, all of these have been explored as potential explanations, and none has given us a definitive answer. The existence of the muon, this uninvited heavy copy of the electron, remains as mysterious today as it was when Rabi asked who ordered it in the 1930s. And yet, despite being mysterious, the muon is real. It is produced constantly in nature. Every second, muons rain down on the surface of Earth, created when cosmic ray protons smash into air molecules high in the atmosphere. These collisions produce pions, and pions decay into muons. The muons then streak toward the ground at nearly the speed of light. Roughly 10,000 muons pass through every square meter of Earth's surface every minute. Right now, as you listen to this, muons are passing through your body. They pass through the walls, through the floor, through the ground beneath you. They barely interact with matter because they are leptons. They don't feel the strong force. They interact only through the electromagnetic force and the weak force, and at the energies they carry, they slip through solid matter with remarkable ease. You are being constantly bathed in particles that shouldn't exist, particles nobody predicted, particles nobody ordered, particles that do nothing obvious, that play no role in the chemistry of your body or the structure of your atoms. They are there, and then they are gone, decaying into lighter particles after their brief 2-microsecond lifetime, leaving almost no trace of their passage. What makes all of this even more extraordinary is what that brief lifetime means. The muon decays, the electron doesn't, and the only difference between them is mass. This single fact, that being heavier makes a particle unstable, is one of the most profound and counterintuitive principles in all of physics. In everyday life, heavier things are more substantial. Heavier things feel more solid, more permanent, more real. A boulder seems more enduring than a pebble. A mountain seems more permanent than a hill. But in particle physics, the opposite is true. Heavier particles are less stable. They decay faster. They exist for shorter times. The more massive you are, the quicker you die. This is because mass is a form of energy, following Einstein's equivalence of mass and energy, and nature always seeks the lowest energy state. A heavy particle sitting alone is a system with a lot of energy concentrated in one place. If there's a way for that energy to redistribute itself into lighter particles, physics demands that it will. The only question is whether the rules of physics, the conservation laws, and the available forces permit the transformation. For the muon, they do. For the electron, they don't. And that single distinction, that one difference in what the rules allow, is why the muon dies and the electron lives. It's why the muon exists for 2 millionths of a second, while the electron, as far as we know, lasts forever. How that works, why the weak force makes it happen, and what the muon actually turns into when it dies, that's where this story goes next. To understand why the muon dies and the electron doesn't, you first need to understand what these two particles truly have in common, and where exactly they diverge. Because the similarities between them are so deep, so precise, so eerily exact, that the single difference between them becomes all the more striking. It's like finding two keys that are identical in every groove, every tooth, every contour, except one key is made of steel and the other is made of lead. They fit the same lock, they turn the same way, but one of them is heavier. And in the world of particle physics, that extra weight changes everything. Both the muon and the electron belong to a family of particles called leptons. This is one of the two great families of matter particles in the Standard Model. The other family is the quarks. Every particle of matter you've ever encountered, every atom, every molecule, every grain of dust and drop of water is built from members of these two families. Quarks combine to form protons and neutrons, which make up atomic nuclei. Leptons include the electrons that orbit those nuclei. Together, quarks and leptons account for all the visible matter in the universe. But these two families are fundamentally different from each other in one critical respect, and understanding that difference is essential to understanding what the muon is and why it behaves the way it does. The difference comes down to which forces each family feels. In the Standard Model, there are four fundamental forces: gravity, which governs the motion of planets and galaxies and holds your feet to the ground; electromagnetism, which holds atoms together, governs chemistry, produces light, and is responsible for virtually every force you experience in daily life, other than gravity; the strong nuclear force, which binds quarks together inside protons and neutrons and holds those protons and neutrons together inside atomic nuclei; and the weak nuclear force, which is responsible for certain types of radioactive decay and plays a crucial role in nuclear reactions inside stars. Every particle interacts with some combination of these forces. What defines a particle, in large part, is which forces it responds to, and this is where quarks and leptons part ways. Quarks feel all four fundamental forces. They feel gravity, electromagnetism, the strong force, and the weak force. They're responsive to everything the universe can throw at them. Leptons, on the other hand, feel gravity, electromagnetism, and the weak force, but they do not feel the strong nuclear force. This distinction is not a minor detail, it's enormous. The strong force is by far the most powerful of the four forces at subatomic scales. It's what glues quarks together so tightly that you can never find a free quark alone in nature. Quarks are always confined inside composite particles like protons and neutrons, bound together by the overwhelming grip of the strong force. Leptons don't experience this. A muon or an electron can exist on its own, free and unattached, wandering through space without being bound to anything. No strong force grabs hold of them, no gluons confine them. They're free agents in a way that quarks can never be. This is why the muon, despite being a subatomic particle, can travel enormous distances through matter. When a muon is created in the upper atmosphere by cosmic ray collisions, it streaks toward the ground at nearly the speed of light. On the way down, it passes through miles of air, through rooftops, through concrete, through rock. It does this because the only forces that can interact with it significantly at these energies are the electromagnetic force and the weak force. The electromagnetic force causes the muon to lose energy gradually as it passes through matter, interacting with the electric fields of atoms it passes near. But it doesn't get grabbed and absorbed the way a particle that feels the strong force would. A pion, which is a composite particle made of quarks and does feel the strong force, gets absorbed rapidly when it enters matter. It interacts violently with atomic nuclei and is destroyed almost immediately. The muon sails through because it simply doesn't speak the language of the strong force. It's deaf to it. The atoms it passes through might as well not be there, at least as far as the strong force is concerned. Now, within the lepton family, there are 6 members, arranged in 3 pairs. Each pair consists of 1 charged lepton and 1 neutrino. The first pair is the electron and the electron neutrino. The second pair is the muon and the muon neutrino. The third pair is the tau and the tau neutrino. These three pairs correspond to the three generations of matter in the Standard Model, and they form one of the most peculiar patterns in all of physics. Each generation is essentially a heavier carbon copy of the one before it. The muon is a heavier version of the electron. The tau is a heavier version of the muon. The same pattern repeats in the quark sector. The charm quark is a heavier version of the up quark. The strange quark is a heavier version of the down quark. The top quark is a heavier version of the charm quark. The bottom quark is a heavier version of the strange quark. 3 generations of quarks, 3 generations of leptons, each generation heavier than the last, and nobody knows why. Let me be precise about the charged leptons because the details matter. The electron has a mass of approximately 0.511 megaelectron volts. The muon has a mass of approximately 105.7 megaelectron volts. The tau has a mass of approximately 1,777 megaelectron volts. These are enormous jumps. The muon is about 207 times heavier than the electron. The tau is about 17 times heavier than the muon, and about 3,490 times heavier than the electron. Each step up the generational ladder multiplies the mass dramatically. And in every other measurable respect, these three particles are identical. Same charge, same spin, same interactions, same forces, same role in every equation, just different masses. This pattern extends to the neutrinos as well, though neutrinos are far more mysterious. Each charged lepton is paired with a corresponding neutrino. The electron pairs with the electron neutrino. The muon pairs with the muon neutrino. The tau pairs with the tau neutrino. Neutrinos are electrically neutral, which means they don't interact through the electromagnetic force at all. They only interact through the weak force and gravity. And gravity is so incredibly weak at the subatomic scale that it's completely irrelevant for particle physics. So neutrinos interact only through the weak force, making them almost invisible. They pass through matter with astonishing ease. Trillions of neutrinos are passing through your body right now, produced by nuclear reactions in the sun, and virtually none of them interact with anything inside you. A neutrino can pass through a light year of solid lead and have roughly a 50-50 chance of being stopped. That's how weakly they interact. Neutrinos have mass, but their masses are incredibly tiny, less than about 1 electron volt based on the most recent direct measurements, millions of times lighter than even the electron. The exact masses haven't been measured yet, and determining them is one of the major goals of modern particle physics. The pairing between charged leptons and neutrinos isn't just for organizational convenience. It reflects a deep structure in the weak force. The weak force connects each charged lepton to its corresponding neutrino. When a muon decays, for example, it produces a muon neutrino, not an electron neutrino or a tau neutrino. This pairing is governed by a conserved quantity called lepton flavor. The electron and the electron neutrino carry electron flavor. The muon and the muon neutrino carry muon flavor. The tau and the tau neutrino carry tau flavor. In most interactions, these flavors are conserved separately. When a muon decays, the total muon flavor and total electron flavor of the products must match the initial state. This is why the muon's decay produces specific combinations of particles rather than arbitrary ones. The conservation laws constrain what's possible. Let's go deeper into what it means for the muon and the electron to be so similar. When physicists say the muon is a heavier version of the electron, they mean something very precise. In the language of quantum field theory, the electron and the muon are described by fields with identical mathematical structure. Both are spin 1/2 Dirac fields. Both transform the same way under the symmetries of the Standard Model. Both carry electric charge -1 in units of the elementary charge. Both couple to the photon with the same strength, determined by the electromagnetic coupling constant. Both couple to the Z boson, the neutral carrier of the weak force, in the same way. Both couple to the W boson, the charged carrier of the weak force, in the same way. If you wrote down the equations governing the electrons' interactions and simply changed the label from electron to muon everywhere, you would get exactly the right equations for the muon, except for one term, the mass term. The mass term is different because the muon field has a different coupling to the Higgs field. This is worth spending time on because it gets at the deepest level of what mass actually is for a fundamental particle. In the original formulation of the Standard Model, before the Higgs mechanism was introduced, all the fundamental particles were massless. The equations that describe their interactions, the beautiful symmetric equations of gauge theory, only work if the particles have zero mass. If you try to simply add mass by hand, you break the mathematical symmetries that make the theory self-consistent. This was a serious problem because we know particles have mass, electrons have mass, muons have mass. The W and Z bosons that carry the weak force have mass. So, where does mass come from if the fundamental equations don't allow it? The answer came in 1964, when several physicists, including Peter Higgs, François Englert, and Robert Brout, proposed a mechanism now called the Higgs mechanism. The Higgs field, as we've already established, fills all of space with a constant background value. That background value is roughly 246 giga-electron-volts, a number called the vacuum expectation value. What matters here is the mechanism. As a particle moves through space, it is constantly interacting with this background. The Higgs field resists the particle's acceleration. It creates inertia. It makes the particle behave in every measurable way as though it has mass. And the strength of this resistance depends entirely on how strongly the particle's own field couples to the Higgs field. Particles that don't couple at all, like the photon, remain massless and travel at light speed. Particles that couple weakly acquire small masses. Particles that couple strongly acquire large masses. The strength of each particle's interaction with the Higgs field is determined by a number called the Yukawa coupling constant. Each fundamental particle has its own Yukawa coupling. The electron's Yukawa coupling is very small, roughly 2.9 times 10 to the minus 6. This gives the electron its tiny mass. The muon's Yukawa coupling is larger, about 6.09 times 10 to the minus 4. This gives the muon its greater mass. The top quark's Yukawa coupling is close to 1, making it the heaviest fundamental particle known, with a mass of about 173 giga-electron-volts. These Yukawa couplings are among the free parameters of the Standard Model. The theory doesn't predict them. They must be measured experimentally and then inserted into the equations. The theory tells you that each particle has a Yukawa coupling, and that this coupling determines the particle's mass, but it doesn't tell you what the value of the coupling is. Why the electron's Yukawa coupling is 2.9 times 10 to the minus 6 rather than some other number is a question the Standard Model cannot answer. Why the muon's Yukawa coupling is about 207 times larger than the electron's is equally mysterious. This is what makes the muon's mass so fascinating and so frustrating. The mass difference between the muon and the electron is real and measurable and precisely known, but the reason for it is completely unknown. The Higgs mechanism tells us how particles get mass. It doesn't tell us why they get the specific masses they do. The mechanism is understood. The parameters that go into it are not. It's like understanding how a piano works, knowing that pressing a key causes a hammer to strike a string and produce a note, but having no idea why the piano has 88 keys instead of 40 or 200. The mechanism is clear. The reason behind the specific configuration is not. The discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed the Higgs mechanism. The Higgs boson is the particle associated with the Higgs field, the excitation that appears when the Higgs field is disturbed. Finding it was one of the greatest triumphs in the history of physics. It confirmed that the Higgs field is real and that the mechanism by which particles acquire mass is correct. But it didn't solve the flavor problem. It didn't tell us why there are 3 generations. It didn't explain the Yukawa couplings. It gave us the keystone of the Standard Model's mass mechanism, but the deeper questions remain wide open. Now let me talk about the forces the muon feels in a bit more detail, because understanding them is essential to understanding why the muon decays. The muon interacts through 2 forces, electromagnetism and the weak nuclear force. Let's take these one at a time. The electromagnetic force is carried by photons. It acts between any particles that carry electric charge. Since the muon has charge -1, exactly the same as the electron, it interacts with photons in exactly the same way the electron does. A muon can emit and absorb photons. It can be deflected by electric and magnetic fields. It can form bound states with positively charged particles, creating exotic atoms called muonic atoms, where a muon replaces an electron in orbit around a nucleus. These muonic atoms are real, and they've been created and studied in laboratories. They behave much like regular atoms, but with important differences because the muon is 207 times heavier than the electron. A heavier particle orbits closer to the nucleus. The muon's orbital radius in a muonic atom is about 207 times smaller than the corresponding electron orbital. This brings the muon much closer to the nucleus, which makes muonic atoms extremely useful for precise measurements of nuclear size and structure. The electromagnetic interaction does not cause the muon to decay. Electromagnetism conserves particle identity. A muon can emit a photon and remain a muon. An electron can emit a photon and remain an electron. The electromagnetic force doesn't change one type of particle into another. It pushes particles around, bends their paths, creates radiation, but it preserves what a particle is. A muon interacting electromagnetically will always remain a muon. The weak force is different. The weak nuclear force is the only force that can change the flavor of a particle, that can transform one type of lepton into another, or one type of quark into another. The weak force is mediated by three particles: the W+ boson, the W- boson, and the Z boson. The Z boson is electrically neutral, and interactions involving the Z boson don't change particle flavor. They're similar to electromagnetic interactions in some ways, but the W bosons carry electric charge, and interactions involving W bosons do change flavor. When a muon interacts with a W boson, the muon can transform into a muon neutrino. The charged lepton becomes its corresponding neutral lepton. This is the fundamental process that underlies muon decay, and it's the reason the muon is unstable. The weak force provides the mechanism. Without the weak force, the muon would be stable. It would last forever, just like the electron. But because the weak force exists, and because the muon is heavy enough for the math to work out, the muon has an escape route. It can transform, it can shed its excess mass, and it can become something lighter. The W and Z bosons are themselves very heavy particles. The W boson has a mass of about 80.4 giga-electron volts, and the Z boson has a mass of about 91.2 giga-electron volts. These are enormous masses by particle physics standards, far heavier than the muon's 105.7 mega-electron volts. The W boson is over 750 times heavier than the muon. This mass has a direct consequence for the strength of the weak force at low energies. The weak force is not intrinsically weak. Its fundamental coupling constant is actually comparable to the electromagnetic coupling constant. The reason we call it the weak force is that its carriers, the W and Z bosons, are so heavy. Because they're heavy, they can only exist as virtual particles for extremely short times before the uncertainty principle demands they disappear. This suppresses the range and apparent strength of the weak force at everyday energies. At very high energies, comparable to the W and Z masses, the weak force is comparable in strength to electromagnetism. But at the low energies relevant for muon decay, where the muon's mass is hundreds of times smaller than the W boson's mass, the weak force is enormously suppressed. It acts, but it acts slowly. Slowly, in particle physics terms, means the muon lives for about 2.2 microseconds. That might sound short by human standards. It's not long enough to blink an eye. But by particle physics standards, it's extraordinarily long. Many particles decay in trillionths or quadrillionths of a second. The muon's 2 microsecond lifetime is almost leisurely by comparison. And the reason is precisely that the weak force is so feeble at the muon's energy scale, suppressed by those massive W bosons that can only appear as fleeting virtual particles. Let me pause here to address something that might seem confusing. The muon is a fundamental particle. It has no internal structure. It is not made of smaller pieces. And yet it decays. It falls apart. How does something with no parts fall apart? In everyday language, decay means breaking into pieces. You imagine a building crumbling, its bricks and beams separating. But that analogy fails completely for fundamental particles. When the muon decays, it does not break into pre-existing components. The particles that emerge from muon decay were not inside the muon waiting to get out. They are created in the process of decay itself. The muon's mass, which is a form of energy, is converted into the mass and kinetic energy of the decay products. This is allowed by Einstein's relationship between mass and energy. Mass can become energy, energy can become mass. This is where one of the most famous lines in the history of physics comes from. When the Nobel laureate Isidor Isaac Rabi heard about this new particle, he reportedly said, "Who ordered that?" It's a perfect reaction. It captures exactly how physicists felt. When the muon decays, its mass energy is redistributed into newly created lighter particles. Nothing breaks apart. Something transforms. The muon ceases to exist, and in its place, new particles appear, conjured from the energy that the muon's mass represented. This process of transformation, rather than disassembly, is fundamental to how particle physics works. It happens constantly in nature. A free neutron, sitting alone outside an atomic nucleus, will decay in about 10 minutes. It transforms into a proton, an electron, and an electron antineutrino. The neutron is a composite particle made of quarks, so in its case, the decay involves one of its down quarks changing into an up quark via the weak force. But the principle is the same. A heavier particle transforms into lighter particles. The weak force mediates the transformation, and the products are not extracted from the original, they are created from the available energy. The key principle governing whether a particle can decay is deceptively simple. A particle can decay if and only if there exist lighter particles into which it can transform without violating any conservation laws. That's it. If lighter particles with the right quantum numbers exist, and if there's a force capable of mediating the transition, the particle will decay. The heavier it is relative to its decay products, the more energy is available for the process, and generally, the faster the decay occurs. The muon can decay because there exist lighter particles with the right quantum numbers. It can transform into an electron, a muon neutrino, and an electron antineutrino. The total charge is conserved. The total lepton number is conserved. The individual lepton flavors are conserved. Everything checks out. The weak force can mediate the transition, so the muon decays. The electron cannot decay because there is nothing lighter for it to become. The electron is the lightest charged particle in existence. There is no particle with charge -1 that has less mass than the electron. For the electron to decay, it would need to produce something lighter than itself, while still conserving electric charge and lepton number. But nothing lighter and appropriately charged exists. The electron is stuck. It sits at the bottom of the mass ladder for charged leptons. There's nowhere for it to go. The conservation laws that permit the muon to decay forbid the electron from doing the same thing. The electron is stable, not because it's built differently, not because it has some special protective quality, not because there's a force holding it together. It's stable because it has nowhere to fall. It's already at the bottom. This asymmetry between the muon and the electron, this fundamental difference in their fates, arises entirely from the difference in their masses. Give the electron more mass, make it heavier than the muon, and suddenly the electron would be the one that decays, and the muon would be stable. The identity of the particle doesn't matter. What matters is the mass relative to available decay products. The heavier particle can always decay into the lighter one, never the reverse. It's one of the most powerful organizing principles in particle physics, and it governs the lifetime and stability of every particle in the universe. Mass, in particle physics, is not just a measure of how heavy something feels or how much it resists being pushed. Mass is destiny. It determines which particles are stable and which are doomed. It determines how quickly an unstable particle will die. It determines which interactions are possible and which are forbidden. It determines the entire life story of a particle, from its creation to its destruction. Two particles can be identical in every other respect. Same charge, same spin, same forces, same quantum numbers. But if one is heavier than the other, their fates diverge completely. The light one endures, the heavy one perishes. This principle doesn't just apply to leptons, it runs through all of particle physics. The top quark, the heaviest quark, decays so fast that it doesn't even have time to form a composite particle. It decays in roughly 5 × 10⁻25 seconds, transforming into a bottom quark and a W boson before the strong force can bind it to anything. The W boson itself is unstable, decaying almost instantly into lighter particles. The Z boson is unstable. The Higgs boson is unstable, with a lifetime of about 1.6 × 10⁻22 seconds. Heavier particles decay faster because more energy is available for the transformation, and the process is correspondingly more vigorous. Lighter particles, if they sit at the bottom of some chain with no lighter alternatives available, are stable. The electron, the lightest charged lepton, is stable. The proton, the lightest baryon, is stable as far as we've ever measured, though some theories predict it might decay with an unfathomably long lifetime. The photon is stable and massless. The lightest neutrino is stable because there's nothing lighter for it to become. Stability in particle physics is not about strength or durability, it's about having nowhere left to fall. And this is the muon's tragedy, if a particle can be said to have a tragedy. It is identical to the electron in every way that matters for function, for interaction, for its role in the equations of physics. It carries the same charge, it feels the same forces, it has the same spin. It would form the same kinds of atoms. It would participate in the same kinds of chemistry. If you could somehow make a muon last forever, you could build atoms with muons instead of electrons. Muonic chemistry would work. Muonic molecules would form. The physics would be different in detail because the muon's greater mass would pull it closer to the nucleus and change the energy levels, but the basic structure would be there. The muon could do everything the electron does, but it can't last. It's too heavy. The weak force provides an exit, a doorway through which the muon's excess energy can escape, and nature always takes that exit. The muon is condemned by its own mass. It is identical to the electron in every quality except the one that determines whether it gets to exist for longer than 2/millionths of a second. This brings us to the doorway itself, the mechanism, the weak force interaction that transforms the muon into lighter particles. Understanding exactly how this process works, step by step, particle by particle, is essential to understanding why the muon dies so quickly and what determines the precise timescale of its death. That mechanism, the actual physics of muon decay, is where we need to go next. The muon dies because it can. That sounds almost too simple to be meaningful, but it is the deepest truth about this particle's fate. The muon has enough mass to transform into lighter particles without violating any conservation law, and the weak nuclear force provides the mechanism to carry out that transformation. The electron, sitting at the bottom of the mass ladder for charged leptons, has no such option. It cannot decay because there is nothing lighter for it to become. The muon can, and so it does, every single time, without exception, in roughly 2.2 microseconds. Understanding exactly how this happens requires following the decay process step by step, from the moment the muon begins to transform to the moment the final products fly apart. And the process reveals something remarkable about the way the universe works at its most fundamental level. Let's set the stage. You have a muon sitting in space. It carries negative electric charge. It has a mass of about 105.7 mega-electron volts. It's spinning, possessing an intrinsic angular momentum of 1/2 in the quantum mechanical units called h-bar. It doesn't feel the strong force. It interacts with the electromagnetic field and the weak field, and it is alone. Nothing is colliding with it. Nothing is disturbing it. No external force is pushing it or pulling it. It's just sitting there, and yet, in about 2.2 microseconds on average, it will cease to exist. It will transform into three other particles: an electron, a muon neutrino, and an electron antineutrino. These three particles will fly away from the point where the muon was, carrying with them all the energy and momentum the muon originally had. The muon is gone. In its place, three lighter particles share the spoils. This process is called muon decay, and it is mediated by the weak nuclear force. Specifically, it proceeds through the exchange of a virtual W boson. Let me explain what that means, because the concept of a virtual particle is one of the most important and most frequently misunderstood ideas in particle physics. In quantum field theory, forces between particles are described as exchanges of other particles. The electromagnetic force between two electrons, for example, is described as the exchange of virtual photons. One electron emits a photon, the other absorbs it, and the exchange creates the effect we perceive as a force. The strong force between quarks is described as the exchange of virtual gluons, and the weak force is described as the exchange of virtual W and Z bosons. The word virtual is doing important work here. A virtual particle is not the same as a real particle. A real particle is one you can detect. It travels through space, carries energy and momentum, and can register in a detector. A real photon is a flash of light. A real electron is a particle that leaves a track in a cloud chamber. Virtual particles are different. They exist only as intermediaries in a process. They pop into existence during an interaction and disappear before the interaction is complete. They are never directly detected. They are mathematical objects that appear in the equations describing how particles interact, representing the way quantum fields mediate forces. Virtual particles can do things real particles cannot. Most importantly for our purposes, a virtual particle does not need to have the same mass as its real counterpart. A real W boson has a mass of about 80.4 giga-electron-volts. If you wanted to create a real W boson, you would need at least 80.4 giga-electron-volts of energy. The muon has a mass of only about 105.7 mega-electron-volts, which is a tiny fraction of the W boson's mass. There is nowhere near enough energy in a muon to create a real W boson. But the muon doesn't need to create a real one. It creates a virtual one. The uncertainty principle allows energy to be borrowed for brief moments. The more energy you borrow, the shorter the time you can borrow it for. A virtual W boson can exist for an incredibly brief instant, far too short to ever be detected directly, but long enough to mediate the decay process. It flickers into existence and then immediately transforms into the decay products, all within a time so short that the borrowed energy is returned before the universe notices the debt. Here is how muon decay proceeds. The muon, carrying negative charge, transforms into a muon neutrino by emitting a virtual W- boson. This is the crucial step. The weak force changes the muon into its partner neutrino, the muon neutrino. The muon's electric charge, -1, is carried away by the W- boson, which has charge -1. The muon neutrino is electrically neutral, so the charge is conserved. The muon is gone now, replaced by a muon neutrino. The virtual W- boson exists for an incomprehensibly short time. Almost immediately, it decays into an electron and an electron antineutrino. The W- boson has charge -1. The electron has charge -1. The electron antineutrino is electrically neutral, so charge is conserved in this step as well. And that's it. The process is complete. The muon has become three particles: a muon neutrino, an electron, and an electron antineutrino. Let me trace the conservation laws through this process carefully, because they are what make the process possible and what determine exactly which particles are produced. Start with electric charge. The muon has charge -1. The final products are an electron with charge -1, a muon neutrino with charge 0, and an electron antineutrino with charge 0. Total charge before, -1. Total charge after, -1 plus 0 plus 0 equals -1. Charge is conserved. Now consider lepton number. In the standard model, each lepton carries a lepton number of +1, and each antilepton carries a lepton number of -1. The muon has lepton number +1. The electron has lepton number +1. The muon neutrino has lepton number +1. The electron antineutrino has lepton number -1. Total lepton number before, +1. Total lepton number after, +1 plus +1 minus 1 equals +1. Lepton number is conserved. Now consider lepton flavor, which is conserved separately for each generation in the standard model at tree level. The muon carries muon flavor +1. The final products include a muon neutrino, which carries muon flavor +1. So muon flavor is conserved. The electron carries electron flavor +1, and the electron antineutrino carries electron flavor -1. So electron flavor is 0 before the decay, and +1 minus 1 equals 0 after. Electron flavor is conserved too. Every conservation law is satisfied. Nothing is violated. The bookkeeping is perfect. The process is allowed, and therefore it happens. Now, notice something critically important about this process. The electron and the neutrinos that emerge from muon decay were not inside the muon. They did not exist before the decay happened. They were created during the process. The virtual W boson materializes them from the available energy. The muon's mass energy, 105.7 MeV, is redistributed into the masses and kinetic energies of the three decay products. The electron has a mass of about 0.511 MeV. The neutrinos have masses so tiny they're negligible for this calculation, less than a few electron volts. So the combined rest mass of the decay products is essentially just the electron's mass, about 0.511 MeV. The muon's mass is 105.7 MeV. That means there is about 105.2 MeV of energy left over after accounting for the rest mass of the products. This leftover energy becomes kinetic energy, the energy of motion, shared among the three particles as they fly apart. This is why the decay products emerge with significant speed. They carry away the muon's excess mass as kinetic energy. The fact that the muon's decay products are created rather than released is one of the most profound aspects of particle physics. It means that decay in the quantum world is fundamentally different from breaking apart in the everyday world. When a glass shatters, the shards were already part of the glass. They existed as structural elements before the breaking. When a muon decays, the electron and neutrinos did not exist before the decay. They are conjured into being from pure energy, sculpted from the mass of the muon by the weak force. The muon doesn't break, it transforms. One particle becomes three particles, and the total energy and momentum are perfectly conserved throughout. This brings us to a question that cuts right to the heart of quantum mechanics. If there's nothing wrong with the muon, if nothing is pushing it, if nothing collides with it, then why does it decay at all? What triggers the transformation? The answer is that nothing triggers it. Muon decay is a spontaneous quantum process. It happens because it can happen, and in quantum mechanics, anything that can happen will happen with some probability. The muon doesn't need a reason to decay. It doesn't need an external push. The near existence of a lower energy final state that the muon can reach through the weak interaction is enough. Quantum mechanics guarantees that the transition will occur. The question is not whether it will happen, but when, and the timing is fundamentally random. This is one of the strangest and most unsettling features of quantum mechanics. The decay of any individual muon is completely unpredictable. You can have two muons created at exactly the same time, in exactly the same conditions, with exactly the same energy, and one might decay after half a microsecond, while the other lasts for 5 microseconds. There is no hidden variable, no internal clock, no structural flaw in the long-lived muon that distinguishes it from the short-lived one. the randomness is genuine. It's not that we lack information about the muon's internal state, it's that there is no information to be had. The muon has no internal state that determines when it will decay. The timing is governed by pure quantum probability. What we can predict is the average. If you start with a large collection of muons, you can predict with extraordinary precision what fraction will have decayed after a given time. The average lifetime of the muon is approximately 2.19703 microseconds. This number has been measured to extraordinary precision in laboratory experiments, and it agrees perfectly with the theoretical prediction from the Standard Model. But any individual muon might decay much sooner or much later than this average. The distribution follows an exponential decay law, the same mathematical pattern that governs radioactive decay. The probability that a muon survives to time t is proportional to e raised to the power of negative t divided by the mean lifetime. This means that after one lifetime, about 36.8% of the original muons remain. After 2 lifetimes, about 13.5% remain. After 3 lifetimes, about 5%. After 10 lifetimes, less than 1/100%. The population dwindles exponentially, each muon decaying independently and randomly. Now let me address the role of the virtual W boson more carefully, because it determines the rate of decay and explains why the muon lives as long as it does. The W boson, as I mentioned, has a mass of about 80.4 giga-electron volts. The muon has a mass of about 105.7 mega-electron volts. The ratio between these masses is roughly 760 to 1. The W boson is 760 times heavier than the muon. This enormous mass disparity has a profound effect on the decay process. In quantum field theory, the probability of a process involving a virtual particle is suppressed when the virtual particle's mass is much larger than the energy available in the interaction. The virtual W boson in muon decay is far heavier than the muon, so the process is heavily suppressed. Think of it this way. The virtual W boson borrows an enormous amount of energy from the vacuum, far more than the muon's mass provides. The uncertainty principle allows this borrowing, but only for an incredibly short time. The heavier the virtual particle, the shorter it can exist, and the more suppressed the process becomes. This suppression is what makes the weak force weak at low energies. It's not that the fundamental coupling is small. The weak coupling constant is actually comparable to the electromagnetic coupling constant, but the massive W boson acts as a bottleneck, throttling the rate of the process. Mathematically, the effect of the heavy W boson is captured by a quantity called the Fermi coupling constant, named after Enrico Fermi, who first described weak decays in the 1930s, before the W boson was even theorized. The Fermi coupling constant, usually written as G sub F, is approximately 1.166 times 10 to the minus 5 per giga-electron volt squared. This tiny number encodes the suppression from the heavy W boson. The decay rate of the muon, the inverse of its lifetime, is proportional to G sub F squared times the fifth power of the muon's mass, divided by a numerical factor involving pi. The fifth power of the muon mass is crucial. It means that the decay rate is extraordinarily sensitive to the muon's mass. If the muon were twice as heavy, everything else being equal, the decay rate would be 32 times faster and the lifetime 32 times shorter. If the muon were 10 times heavier, the decay rate would be 100,000 times faster. This dramatic sensitivity to mass is why heavier particles generally decay faster. The more mass they have, the more energy is available for the decay process, and the faster the transition proceeds. The fifth power dependence on mass deserves some explanation, because it reveals how the physics works at a deeper level. In muon decay, the final state contains 3 particles: the electron, the muon neutrino, and the electron antineutrino all share the available energy. The amount of energy available is essentially the muon's mass, since the decay products have negligible mass by comparison. The more energy available, the more ways the 3 particles can share it, and the more possible final states there are. In quantum mechanics, a process happens faster when there are more possible final states, because each possible state represents an independent pathway for the process to occur, and the total probability is the sum of all pathways. The number of available final states grows rapidly with the available energy. For a three-body decay like the muons, the phase space, which is the technical term for the number of available final states, grows as the fifth power of the available energy. More energy means vastly more pathways, which means a vastly higher decay rate. This is the fundamental reason why heavier particles die faster. It's not that the force acting on them is stronger. The weak force coupling is the same for all leptons. It's not that heavier particles are less stable in some structural sense, as though they were shoddily constructed. The muon is a point particle with no structure. It's that heavier particles have more energy to distribute among their decay products, which means more available final states, which means a higher probability of decay per unit time. The muon's mass doesn't make it fragile, it makes its death probable. Every extra bit of mass opens up new pathways for the energy to escape, and each new pathway increases the rate at which the muon transforms. Let me put some numbers to this to make it concrete. The muon's mass is about 105.7 mega-electron volts. The electron's mass is about 0.511 mega-electron volts. The mass difference is about 105.2 mega-electron volts. This energy is distributed among the three decay products as both rest mass and kinetic energy. The electron, being the only massive product, can carry anywhere from 0 to about 52.8 mega-electron volts of kinetic energy, depending on the specific configuration of the decay. The two neutrinos share the remaining energy. Because there are three particles in the final state, and they can share the energy in many different ways, the electron doesn't always come out with the same energy. Sometimes it's fast, sometimes it's slow. The distribution of electron energies follows a specific curve predicted by the Standard Model, called the Michel spectrum, named after Louis Michel, who first calculated it. The Michel spectrum has a distinctive shape. Within that allowed energy range, the distribution is far from uniform. The spectrum rises steeply toward the high-energy end. Electrons near the maximum energy are far more common than electrons near zero energy. This shape is not arbitrary, it's a direct consequence of how the weak force operates, specifically its preference for certain spin orientations. The weak force is unusual among the fundamental forces because it violates parity symmetry, meaning it distinguishes between left-handed and right-handed particles. This preference sculpts the energy distribution of the decay products in a very specific way. If the weak force worked differently, if it treated left and right equally, the Michel spectrum would have a different shape. So by measuring the energy distribution of electrons from muon decay with high precision, physicists can test whether the weak force behaves exactly as the Standard Model predicts. Every deviation, no matter how slight, would signal something new. So far, the measured spectrum matches the prediction with extraordinary fidelity, confirming the Standard Model's description of the weak interaction at a very detailed level. This spectrum has been measured in experiments with exquisite precision, and it matches the theoretical prediction beautifully. The agreement is one of the great successes of the Standard Model's description of the weak interaction. The fact that three particles are produced rather than two has important consequences. When a particle decays into exactly two products, the conservation of energy and momentum completely determines the energies of both products. Each product comes out with a single, fixed energy every time. But when a particle decays into three products, the conservation laws leave freedom. The energy can be distributed in many different ways among the three particles. This is why the electron from muon decay has a range of possible energies rather than a single fixed energy. It's also why the decay process has such a large phase space, contributing to that fifth power dependence on mass. Now, you might wonder whether the muon could decay through some other channel. Could it decay into just an electron and a photon, for example? This would be simpler, a two-body decay with easily predicted kinematics, and the conservation of charge and total lepton number would be satisfied. The muon has charge -1, the electron has charge -1, and the photon has charge 0. Total lepton number is +1 before and +1 after. It looks like it should work, but it doesn't happen. In the Standard Model, the decay of a muon directly into an electron and a photon is forbidden because it violates lepton flavor conservation. The muon carries muon flavor, and the electron carries electron flavor. For this decay to occur, muon flavor would have to be destroyed and electron flavor created, with nothing to balance the books. There's no muon neutrino to carry away the muon flavor, and no electron antineutrino to cancel the electron flavor. The transaction doesn't balance, so the Standard Model forbids it. This is actually a very important prediction. If someone ever observes a muon decaying directly into an electron and a photon, it would be evidence that the Standard Model is incomplete, that there are new particles or forces beyond what we currently know. Several major experiments, including the MEG experiment at the Paul Scherrer Institute in Switzerland, have searched for this forbidden decay with extraordinary sensitivity. They've examined trillions of muon decays, looking for even a single instance of a muon becoming an electron and a photon. So far, none has been found. The current upper limit on the probability of this decay is about 3.1 times 10 to the minus 13. That means, if this process happens at all, it happens less than once in every 3 trillion decays. This incredibly tight limit is one of the strongest constraints on new physics beyond the Standard Model. There are theoretical extensions of the Standard Model involving new particles or new symmetries that would allow tiny violations of lepton flavor conservation. In these theories, the muon could occasionally decay into an electron and a photon, but with an extremely small probability. Finding such a decay would be a landmark discovery, a crack in the Standard Model pointing toward deeper physics. The search continues. Let me return to the main decay channel and emphasize what it tells us about the nature of the weak force. The weak force is the only fundamental force that changes particle identity. Electromagnetism doesn't do this. When an electron emits a photon, it remains an electron. The strong force doesn't do this either, at least not for lepton flavors. Only the weak force reaches into a particle and transforms it into something else. This is remarkable when you think about it. Most forces in nature push and pull. They accelerate, they attract, they repel. The weak force does something qualitatively different. It transforms. It turns one particle into another. A muon becomes a muon neutrino. A down quark becomes an up quark. A neutron becomes a proton. The weak force is the alchemist of particle physics, transmuting one form of matter into another. And the weak force does this with perfect democracy among the generations, at least in principle. The coupling of the weak force to the muon is exactly the same as its coupling to the electron, and exactly the same as its coupling to the tau. The W boson doesn't care which generation a lepton belongs to. It treats them all the same. The difference in decay rates between the muon and the tau doesn't come from a difference in how strongly the weak force acts on them. It comes entirely from the difference in their masses through that fifth power relationship. The tau, being about 17 times heavier than the muon, has far more energy available for decay. The fifth power mass scaling predicts the tau's leptonic decay rate alone should be roughly 1,400,000 times faster than the muons. But the tau is also heavy enough to decay into hadrons, combinations of quarks produced through the weak force, something the lighter muon cannot do. These additional decay channels accelerate its destruction further. The tau's measured lifetime is about 2.9 times 10 to the minus 13 seconds, roughly 7.5 million times shorter than the muons. Mass remains the dominant factor, but the extra decay channels available to heavier particles compound the effect. This fifth power scaling law is one of the most powerful predictions of the Standard Model. It tells you that mass is the dominant factor controlling how quickly a particle decays through the weak interaction. Everything else, the coupling constants, the numerical factors, the details of the W boson propagator, all of these are the same for every lepton. Mass is what differs. Mass is what matters. Mass is what determines how long you live. And this leads to a profound and almost philosophical point about the relationship between mass and stability in the quantum world. In our everyday experience, massive things are durable. Heavy objects are hard to break. A stone wall is more durable than a paper wall. A steel beam is sturdier than a wooden plank. We associate mass with permanence, with solidity, with resistance to destruction. But in particle physics, the opposite is true. The heavier you are, the faster you die. Mass is not a source of stability. Mass is a source of instability. It's a reservoir of energy, and energy always seeks to disperse itself into the most probable configuration. A heavy particle sitting alone is an improbable concentration of energy. A bunch of lighter particles sharing that same energy among themselves is a far more probable state. And quantum mechanics relentlessly drives systems from improbable states toward probable ones. The muon, with its 105.7 mega-electron volts of mass energy, is a concentrated, improbable state. The collection of lighter particles it can decay into is a dispersed, probable state. The transition from one to the other is not just allowed, it is, in a deep thermodynamic and quantum mechanical sense, inevitable. The electron escapes this fate only because there is no dispersed state available to it. It cannot spread its energy into lighter charged particles because none exist. It's already the lightest option. The electron is stable not because it's in a probable state, but because there's no more probable state for it to transition to. It's at the bottom. It has nowhere to fall. If somehow a lighter charged lepton existed, the electron would decay into it just as surely and just as inexorably as the muon decays into the electron. Stability in the quantum world is not a sign of strength or perfection. It's a sign of having no remaining options. There is a beautiful analogy here with energy levels in an atom, which may help make this intuitive. An electron in an atom can occupy various energy levels. If it's in a high energy level, an excited state, it will eventually drop to a lower energy level, emitting a photon as it falls. The process is spontaneous. Nothing pushes the electron down. It simply can transition to a lower state, and quantum mechanics guarantees that it will, after some average time. But if the electron is already in the lowest energy level, the ground state, it cannot fall any further. There is no lower state available, so it stays where it is, indefinitely. The electron in the ground state is stable because it has exhausted all its options for losing energy. The muon is like an electron in an excited state. Its mass places it at a high energy level relative to the lighter particles it could become. Quantum mechanics drives it downward, toward lighter products, shedding energy as it goes. The electron is like an electron already in the ground state. There's no lower level available, no lighter charged lepton to decay into, so it remains stable forever. You can push this analogy a step further to make it even more vivid. Imagine a ball sitting on a staircase. If the ball is on the 5th step, it can roll down to the 4th step, then the 3rd, then the 2nd, then the 1st, losing energy at each step until it reaches the ground floor. At every step, gravity provides the force, and the ball's height provides the available energy. Once the ball reaches the ground floor, it stops. Not because gravity has stopped acting on it, gravity is still pulling just as hard, but because there is no lower step to fall to. The floor is the end. The muon is the ball on a higher step. Its mass is its height. The weak force is gravity, always pulling, always ready to facilitate a fall. And the electron is the ground floor. The muon rolls down, shedding its excess energy as it produces an electron and 2 neutrinos. But the electron itself is already on the ground floor. The weak force is still there, still acting, still perfectly capable of mediating a transition. But there is no step below. No lighter charged lepton exists. The electron has nowhere to fall, so it stays where it is. Not because it's held up, but because down doesn't exist. This analogy is more than a metaphor. The mathematics is closely related. The spontaneous decay of an excited atomic state and the spontaneous decay of the muon are both described by quantum transition amplitudes, calculated using the same fundamental principles of quantum mechanics. The details differ, the forces involved are different, the energy scales are different, but the underlying logic is the same. A system in a higher energy state with access to a lower energy state, will transition spontaneously with a probability per unit time determined by the coupling strength and the density of available final states. That is what the muon does. It transitions, it falls, it sheds its excess mass and becomes the lightest thing it can become, an electron, accompanied by two neutrinos to carry away the remaining energy and satisfy the conservation laws. Every muon, everywhere in the universe, does exactly this. Every muon created in a cosmic ray shower in Earth's atmosphere, every muon produced in a particle accelerator, every muon generated in the decay of a pion anywhere in the cosmos, all of them live for roughly 2.2 microseconds on average, and then they transform into an electron and two neutrinos. The process is universal, identical, governed by exactly the same physics, regardless of where or when the muon was created. And this universality is itself remarkable. It tells us that the laws of physics, particularly the weak interaction, are exactly the same everywhere. A muon produced at the Large Hadron Collider in Geneva decays in the same way, with the same lifetime, as a muon produced in a distant supernova billions of light years away. The weak force doesn't vary from place to place. The Fermi coupling constant doesn't change with time. The physics is uniform and absolute, tested and confirmed by decades of precision measurement. The muon's death, as brief and seemingly insignificant as it is, confirms the universality of the laws governing the quantum world. It is a tiny clock, ticking at exactly the same rate everywhere in the cosmos, and then stopping, always in the same way, always producing the same three particles, always obeying the same conservation laws. The muon dies because it is heavy enough to decay, and because the weak force is there to carry out the sentence. But the precision and the universality of that death tell us something deep about the unity and consistency of the physical laws that govern everything. 2.2 microseconds. That is how long a muon lives on average before it transforms into an electron and two neutrinos. 2.2 millionths of a second. To appreciate how short this is, consider that in the time it takes you to blink your eye, roughly 300 milliseconds, about 136,000 muon lifetimes have elapsed. A camera flash lasts about 1 millisecond. In that single flash, roughly 455 muon generations could have lived and died. The muon's life is breathtakingly short by any human measure, and yet, by the standards of particle physics, 2.2 microseconds is an eternity. To understand why, you need to appreciate the timescales on which other unstable particles exist. The tau lepton, the muon's heavier cousin in the third generation, lives for about 2.9 times 10 to the minus 13 seconds, roughly 7.5 million times shorter than the muon's lifetime. The W boson lives for about 3 times 10 to the minus 25 seconds. Light, travelling at 300,000 kilometers per second, covers less than 1/10 of a femtometer in the time a W boson exists. The Higgs boson lives for about 1.6 times 10 to the minus 22 seconds. Compared to these particles, the muon is practically immortal. It lives long enough to travel measurable distances, to be tracked in detectors, to be studied in exquisite detail. Most unstable particles live and die within the confines of a single atomic nucleus. The muon can cross entire mountains. The precise value of the muon's lifetime has been measured with remarkable accuracy. The current best measurement is 2.1969803 microseconds, plus or minus about 2 picoseconds. That is a precision of about 1 part in a million. This measurement comes from experiments at major particle physics laboratories, primarily at the Paul Scherrer Institute in Switzerland, where enormous numbers of muons are produced, brought to rest in a target, and then observed as they decay. The theoretical prediction from the Standard Model agrees with this measurement beautifully, confirming that our understanding of the weak interaction and the muon's place within it is correct at a very deep level. But why is the muon's lifetime 2.2 microseconds and not, say, 2 nanoseconds or 2 milliseconds? What sets this particular timescale? The answer lies in the interplay between the muon's mass, the strength of the weak force, and the enormous mass of the W boson that mediates the decay. The decay rate of the muon depends on the Fermi coupling constant squared, times the muon mass to the 5th power, divided by a numerical factor involving powers of pi. The Fermi coupling constant itself is determined by the fundamental weak coupling constant and the W boson mass. The W boson is very heavy, about 80.4 giga-electron-volts, and its mass enters the formula to the 4th power in the denominator. This enormous number dramatically suppresses the decay rate. If the W boson were lighter, the muon would decay much faster. If the W boson were heavier, the muon would live even longer. The muon's lifetime is a direct reflection of the W boson's mass. It's a window into the properties of a particle over 750 times heavier than itself. This is one of the remarkable things about particle physics. By measuring the lifetime of the muon very precisely, you can extract information about particles you never directly observe in the decay. The virtual W boson is never seen. It exists only as a fleeting quantum fluctuation. But its presence is felt through the decay rate. The muon's lifetime is like a shadow cast by the W boson. You never see the object directly, but you can measure its shadow with extraordinary precision, and from that shadow, you can deduce the object's properties. Historically, this is exactly how physicists first estimated the mass of the W boson, decades before it was directly discovered. When the W boson was finally discovered at CERN in 1983, its measured mass agreed perfectly with predictions from muon and other weak decay measurements. The muon had been telling us about the W boson all along. Now, there is a spectacular real-world consequence of the muon's lifetime that brings together particle physics and Einstein's theory of special relativity. It involves muons created by cosmic rays. High-energy protons from space strike molecules in Earth's upper atmosphere at altitudes of about 15 to 25 kilometers. These collisions produce pions, which quickly decay into muons and muon neutrinos. The muons then stream downward toward Earth's surface at speeds very close to the speed of light, typically 99.8% or more. Consider the problem. Even traveling at the speed of light, a muon can cover only about 660 meters in 2.2 microseconds. Most muons are created at altitudes of 15 kilometers or more. By ordinary reasoning, essentially no muons should reach the ground. And yet, muons reach the ground in enormous numbers, the same relentless flux raining down on every square meter of the planet. They are detected routinely in physics laboratories around the world. The resolution is time dilation, one of the most striking predictions of Einstein's special theory of relativity. When an object moves at a speed close to the speed of light, time passes more slowly for that object relative to a stationary observer. This is not an illusion. Time genuinely runs slower for the moving object. A muon travelling at 99.8% of light speed experiences time at roughly 1/15 the rate we do on the ground. From the muon's perspective, it lives its normal 2.2 microseconds. But from our perspective, the muon appears to live about 15 times longer, roughly 33 microseconds, enough time to travel about 10 kilometers. The exponential distribution means some muons live several times this dilated lifetime, enough to cover 20 or 30 kilometers and reach the ground comfortably. This has been measured directly. In a classic experiment performed in 1963 by David Frisch and James Smith, muons were counted at the top of Mount Washington in New Hampshire and again at sea level. The method was elegantly simple. They placed a muon detector at the summit, counted how many muons arrived per hour within a specific energy range, and then placed an identical detector at sea level and counted again. By selecting muons within a narrow speed range, they could calculate exactly how long the journey from mountaintop to sea level should take. They knew the muon's lifetime from laboratory measurements. They knew the distance. They could predict precisely how many muons should survive the trip if time dilation did not exist. Then they compared that prediction to what they actually observed. Without time dilation, only about 27 muons should have survived the trip for every 568 detected at the top, but about 412 survived, matching the prediction of special relativity almost exactly. From the muon's own reference frame, it's not living longer, but the distance to the ground is contracted by length contraction, the spatial counterpart to time dilation. Both explanations give exactly the same answer. Every muon that passes through your body is a small proof of time dilation. Let me dwell on the length contraction perspective for a moment, because it is equally extraordinary and often overlooked. From our perspective on the ground, the explanation is time dilation. The muon's clock runs slow, so it lives long enough to reach us. But from the muon's own perspective, its clock runs at a perfectly normal rate. It lives for its usual 2.2 microseconds. Nothing strange happens to its internal experience of time. Instead, what changes is space. From the muon's reference frame, it is essentially stationary, and the Earth is rushing upward toward it at 99.8% of the speed of light. At that speed, the distance between the upper atmosphere and the ground is length contracted. 15 kilometers as measured by us on the ground contracts to roughly 1 kilometer as measured in the muon's frame. The muon doesn't need to live longer. It only needs to cross 1 kilometer, and at nearly the speed of light, that takes far less than 2.2 microseconds. The muon arrives at the ground comfortably within its natural lifetime. The remarkable thing is that both descriptions are equally valid. Neither is more correct than the other. From the ground, time dilation saves the muon. From the muon's frame, length contraction saves it. They are two faces of the same relativistic coin, and the muon's journey from the upper atmosphere to the ground is one of the cleanest demonstrations of this equivalence that nature provides. The muon's relatively long lifetime and its ability to penetrate matter have made it useful for remarkable practical applications. One of the most striking is muon tomography, which uses cosmic ray muons to image the interiors of large structures. When a muon passes through matter, it is deflected slightly by atomic nuclei. Denser materials deflect muons more. By placing detectors around an object and tracking deflections, you can build a three-dimensional image of the object's interior. In 2017, physicists used muon tomography to discover a previously unknown large void inside the Great Pyramid of Giza, at least 30 meters long, hidden above the ground gallery and sealed for over 4,500 years. The technique has also been used to image the interiors of volcanoes, inspect nuclear reactor vessels, and scan cargo containers for hidden nuclear material. Beyond practical applications, the muon has become one of the most important tools for testing the limits of the Standard Model. The most famous example is the muon's anomalous magnetic moment, often called G-2. Every charged particle with spin acts like a tiny magnet, characterized by a G factor. For a simple point particle, the G factor is exactly 2, but interactions with the quantum vacuum modify it slightly, making it a tiny bit larger than 2. This difference can be both calculated from the Standard Model and measured with extraordinary precision. The reason the quantum vacuum modifies the G factor is fascinating and worth understanding intuitively. A muon moving through space is never truly alone. The quantum vacuum around it is seething with activity. Virtual particles, photons, electron-positron pairs, quark-antiquark pairs, W bosons, Z bosons, even virtual Higgs bosons are constantly flickering into existence and vanishing again in the muon's immediate vicinity. These virtual particles form a cloud around the muon, briefly interacting with it before disappearing. Each interaction nudges the muon's magnetic properties slightly. A virtual photon emitted and reabsorbed by the muon changes its effective magnetism by a tiny amount. A virtual electron-positron pair, appearing near the muon and briefly screening its charge, alters the magnetic moment further. Each type of virtual particle contributes its own tiny correction. When you add up all these corrections, calculated to extraordinary precision using the mathematical techniques of quantum field theory, you get the anomalous magnetic moment. The Standard Model prediction includes contributions from electromagnetism, the weak force, and the strong force, each computed separately and added together. The electromagnetic contribution dominates and is known to incredible accuracy. The weak contribution is smaller but well understood. The strong force contribution is the hardest to calculate and is where most of the theoretical uncertainty lies. The muon is ideal for this measurement because its mass makes it about 43,000 times more sensitive than the electron to the effects of heavy, unknown virtual particles. If there are undiscovered particles lurking beyond the standard model, their virtual effects would show up more prominently in the muons G-2 than in the electrons. The muon G-2 experiment at Fermilab injects muons into a large ring-shaped magnet about 14 meters in diameter and watches how the muon's spin axis precesses. Results published in 2021 showed a small but persistent discrepancy between the measured value and certain standard model predictions, roughly 2.5 parts per billion. Whether this discrepancy is real or an artifact of theoretical uncertainty remains actively debated. If real, it could be evidence for new particles or forces beyond the standard model. This brings us to what is perhaps the deepest mystery surrounding the muon. Not how it decays, which we understand precisely. Not how long it lives, which we've measured to extraordinary accuracy. But why it exists at all. Why does nature contain a heavier copy of the electron? What purpose does the muon serve? The standard model does not answer this. It can accommodate any number of generations of matter. 3 is simply what nature chose, and the standard model accepts this as an input without explanation. We know from experiments at the Large Electron-Positron Collider at CERN in the early 1990s that there are exactly 3 generations of light neutrinos, meaning exactly 3 generations of matter. But why 3? Some theoretical frameworks offer partial hints. Certain string theory constructions naturally produce 3 generations from the geometry of extra dimensions. If the extra dimensions have a certain topological property called the Euler characteristic, the number of generations equals half the absolute value of this characteristic. For certain 6-dimensional Calabi-Yau manifolds, this can give exactly 3. But these are specific constructions, not unique predictions. The theory doesn't single out 3 as the only possibility. The muon's existence is connected to other deep puzzles. One is the origin of matter in the universe. The fundamental laws of physics treat matter and antimatter almost symmetrically, yet the universe is made almost entirely of matter. Something broke this symmetry in the early universe. One of the conditions for this symmetry breaking, identified by Andrei Sakharov in 1967, requires certain symmetry violations. With fewer than 3 generations of matter, certain necessary symmetry breaking effects vanish. 3 is the minimum number of generations needed for the standard model to allow any matter-antimatter asymmetry through one particular mechanism involving quark mixing. Whether this fully explains the observed asymmetry is still debated, but the connection is suggestive. Think about what this means. If the universe had only 1 generation of matter, if the electron and the up and down quarks were all that existed, certain symmetry-violating effects in the weak interaction would vanish mathematically. With 2 generations, the effects become possible, but are still insufficient in a specific technical sense. Only with 3 or more generations does the mathematics of quark mixing, described by a structure called the CKM matrix, allow for a particular kind of asymmetry between matter and antimatter, called CP violation. 3 generations is the threshold. Below it, the universe might have remained perfectly symmetric, matter and antimatter annihilating completely, leaving nothing but radiation. No atoms, no stars, no planets, no life. The muon, as the charged lepton of the 2nd generation, is part of the minimum package the universe apparently needed to break the symmetry between matter and antimatter. Its existence might not be an accident or a redundancy. It might be a structural requirement for a universe that contains anything at all. The muon's existence, as part of the 2nd generation, might be linked to the very reason matter exists. There is also the puzzle of the mass hierarchy. The Yukawa couplings that determine particle masses span an enormous range, covering at least 12 orders of magnitude, from the heaviest quark to the lightest neutrino. Why does each generation weigh more than the last? Is there a formula or symmetry that generates these numbers? Many theorists have proposed relationships between the masses, but none is precise enough to be considered a genuine explanation. The muon's mass, 105.7 mega-electron volts, sits in the middle of this hierarchy, its particular value unexplained. And so we come back to where we started. What is a muon actually made of, and why does it die so fast? The answer to the first question is that the muon, as far as every experiment ever conducted can determine, is not made of anything. It is a fundamental particle, a point-like excitation of the muon quantum field, with no known internal structure. The only difference from the electron is mass. The muon field couples more strongly to the Higgs field, and this gives the muon its greater mass. But why this coupling is stronger, why the muon field exists at all as a separate entity from the electron field, these are questions we cannot yet answer. The answer to the second question is that the muon dies so fast because its mass gives it access to a lower energy state. The muon is heavy enough to decay into an electron and two neutrinos through the weak interaction, and the laws of quantum mechanics guarantee that any such transition will occur spontaneously. The rate of decay is determined by the muon's mass, the strength of the weak force, and the mass of the W boson. Every factor conspires to give the muon a lifetime of about 2.2 microseconds, a number calculated from first principles and confirmed by precision measurement to extraordinary accuracy. The muon has taught us enormous amounts about the fundamental workings of nature. Its discovery revealed that the universe contains copies of matter we didn't ask for and still can't explain. Its decay confirmed the structure of the weak force and allowed us to measure properties of particles we couldn't yet directly produce. Its cosmic ray cousins provided some of the first direct evidence for Einstein's time dilation. Its anomalous magnetic moment has become one of the most sensitive probes for physics beyond the standard model. And its very existence reminds us that our understanding of nature, as precise and powerful as it is, remains fundamentally incomplete. The muon is identical to the electron in nearly every respect. It feels the same forces, it obeys the same equations, it carries the same charge, but it weighs 207 times more, and that single difference means the electron persists forever, while the muon vanishes in 2/millionths of a second. Mass is destiny in the quantum world. The electron sits at the bottom of the charged lepton mass ladder with nowhere to fall. The muon sits one rung above, and the weak force provides a staircase down. Nature does not tolerate excess energy concentrated in one place when there exists a pathway to redistribute it. The muon has such a pathway, so it takes it, every single time, without exception. It lives long enough to cross a mountain, to pass through your body, to reveal hidden chambers inside ancient pyramids. But it does not live long enough to build anything permanent. It does not form lasting atoms. It does not participate in chemistry. It appears, it flies, it illuminates whatever it passes through, and then it is gone. A brilliant, fleeting spark of matter, identical to the electron in every way except the one way that matters most. And perhaps the deepest thing the muon teaches us is this: the universe is not minimalist. It did not build reality with the fewest possible components. It created 3 generations of matter where one would have sufficed for atoms, chemistry, and life. It created the muon and the tau, heavier siblings of the electron that serve no obvious structural purpose. The muon is proof that nature has depths we haven't fathomed, patterns we haven't decoded, and reasons we haven't uncovered. Isidore Rabi asked who ordered the muon nearly 90 years ago, and we still don't know. But the question itself, the fact that we can ask it, the fact that we've measured the muon's properties to 10 significant figures, while still being unable to explain why it exists, tells us something important. It tells us that the standard model, magnificent as it is not the final word. There is something deeper, something that explains the generations, that predicts the masses, that tells us why the muon is 207 times heavier than the electron and not some other number. That theory, whatever it turns out to be, will answer Rabi's question at last. And when it does, the muon, this brief, brilliant, uninvited particle, will have played a central role in leading us there.